Couplings for power transmission drives are used when the shafts of rotating equipment must be connected coaxially. That is, when the axis of one shaft must be in line with the axis of another shaft. This is done, for example, when a motor must be attached to driven equipment, like a gearbox or a pump. Making sure the shafts and couplings are precisely aligned is important, because when coupled shafts are out of alignment, the coupling, the shafts, the bearings, and the connected equipment may all be damaged. In industry, many of the failures of rotating equipment are the result of misalignment. Shafts can be misaligned in 3 different ways. First, there is parallel misalignment. This is where the shafts are not lying along the same center line. One may be higher or lower than the other, or off to one side. Angular misalignment may also occur. This happens when 2 shafts intersect at an angle to each other. Most often, misalignment is a combination of these two. Compound misalignment. Coupling alignment is most successful when a step-by-step procedure is used. The measurements that must be made to detect misalignment are not difficult, and the adjustments that must be made to correct misalignment are straightforward. However, the procedures for measuring and adjusting must be done in a particular order. If not, they may have to be repeated many times before satisfactory alignment can be achieved. Now, for this demonstration, nothing's connected to power, so there's nothing to be locked out. But in the real world, whether you're working on a new installation or realigning an existing installation, the first step must always be to make sure that all the equipment you're working on is properly locked out. Then make sure the base plate, feet, or mounting pads of both the driven unit and the driver unit are clean, free of burrs, rust, and dirt. All 4 feet of the driven unit must rest firmly on the base plate. You can check this by trying to rock the unit, or by trying to run a single thin blade of a feeler gauge under each foot. If the unit is not quite flush, do not attempt to correct it just by tightening the retaining bolts. This creates unnecessary stress on the frame, and it may even warp it. In addition, it may produce soft foot, in which just loosening a bolt will cause the driver and driven units to become misaligned. Instead, add shims under the unit until it rests solidly on all 4 feet. Then tighten all the retaining bolts. The driver unit should be slightly lower than the driven unit. During the alignment procedure, one of the units will be raised, and the driver is almost always easier to adjust. If the holes for the driver's retaining bolts haven't already been drilled, set the driver approximately in place so that you can mark where the holes go. Some couplings require specific clearances between the 2 flanges when they are installed. So before drilling holes for the driver's bolts, be sure to check the coupling's data sheet to determine the correct clearance. Adjust the position of the driver so that you have the correct clearance before you mark and drill the holes. The holes are normally drilled about 1/8 of an inch larger than the bolt to allow for adjustment. If you are installing rigid couplings, as we are using here, then one of the coupling flanges will have to be pushed back up the shaft. Leave just enough clearance between the 2 faces for your measurements. 2 different methods are commonly used to align couplings: the straight edge and feeler gauge method and the dial indicator method. This program demonstrates both. Using a straight edge and feeler gauge is not as accurate as the dial indicator method. However, in many applications, using a straight edge and feeler gauge will give adequate results. With practice and experience, it can be performed in about half an hour. The dial indicator method, on the other hand, gives greater accuracy, but it may take 2 to 3 hours to perform. When time permits, the dial indicator method is preferred. No matter which method you use, start by placing the driver into position with the retaining bolts loosely in place but not tightened. From the top view, visually line up the driver as close as you can. You can use a straight edge to help line up the 2 halves of the coupling. If the motor must be raised, add shims under the feet, but remember to leave the coupling flange on the driver unit or motor slightly lower than the coupling flange on the driven unit. When doing this initial positioning, don't use smaller retaining bolts just to get a little more clearance. The smaller bolt may not be strong enough to hold the motor in place during operation. Instead, ream out the holes if more clearance is necessary. Before starting the alignment procedure itself, you should make a quick check to see if the flanges run true. That is, if the shafts are straight and if the coupling flanges are properly mounted. These conditions can be detected by laying a straight edge across one of the flange rims then slowly rotating the other flange. Repeat the procedure for the other flange. Any in and out or up and down motion between the straight edge and the rim of the flange indicates that the shaft is bent or that the flange itself is seated at an angle on the shaft. Either of these conditions will have to be corrected before the alignment can proceed. We are now ready for the first step in a 5-step technique for using a straight edge and feeler gauge. The first step is to remove any angular misalignment as seen from the side view. Angular misalignment is present if the gap between the flange faces forms an angle. If the angle is wider at the top, the back of the motor is too low and it will have to be shimmed up. If the angle is wider at the bottom, the front of the motor is too low and it will have to be shimmed up. If we measure the gap at the top and the gap at the bottom, we know which is wider, and we can also calculate the thickness of the shims we'll need. Insert the strips of the feeler gauge into the gap between the flanges at the top. Make sure you keep the feeler strips straight. Add or subtract feeler strips until they fit snugly without forcing. To determine the gap, add up the thicknesses marked on each strip. Use the feeler gauge to determine the gap at the bottom. The combined thicknesses of the feeler strips you had to add or subtract at the bottom is the difference between the gaps. In this case, we had to add 28 thousandths of an inch. That means the gap at the bottom was wider, so we'll have to add shims to the front of the motor. To determine how thick the shim should be, we need two measurements: the distance between the front and back retaining bolts on the motor, and the diameter of the coupling flange. In this case, the distance between the bolt centers is 5 inches, and the diameter of the coupling flange is 4 inches. To calculate the size of the shims, divide the distance between the bolts, which in this case is 5 inches, by the diameter of the flange, which in this case is 4 inches. 5 inches divided by 4 inches is 1 1/4, or 1.25. To calculate the size of the shims you'll need, multiply this number, 1.25, times the gap difference, 28 thousandths. 28 thousandths times 1.25 is 35 thousandths. So you'll need shims 35 thousandths of an inch thick to go under the front of the motor. If pre-cut stainless steel shims are not available, thin shims can be cut from sheet metal, and thick shims can be cut from flat bar stock. Very thin shims can be cut from a roll of shim stock. Cut the shims in a U shape, just large enough to slide around the bolts. Mark the thickness on each shim with a felt marker so they don't get mixed up. Smooth out any burrs or rough edges. Then slide the shims in place and tighten all bolts just enough to compress the shims. Now check the gaps again. If the top and bottom measurements are not within the tolerance required by the operation, repeat step 1. Typical tolerances may vary several hundredths of an inch to a few 10,000ths of an inch. Make sure you know how precise the alignment must be. Once you have the correct angular alignment from the side view, you can move on to step 2, correcting parallel misalignment as seen from the side view. In this step, the driver must be raised, so make sure it's lower than the driven unit. If it's not, and if only a few thousandths of an inch are involved, the feet or base plate of the driver unit may be machined down to make it lower. The base the driver sits on could be lowered, but this is usually difficult. In this case, since the driven unit is higher, lay the straight edge along the top of the driven flange rim and measure the gap between the straight edge and the driver's flange rim. In this case, it's 10 thousandths of an inch, so the driver must be raised that distance. To do this, add shims 10 thousandths of an inch thick under each of the 4 feet. Be sure to keep any existing shims in place. Tighten all the retaining bolts, then recheck with a straight edge and feeler gauge. Both couplings should now be level with each other. If they aren't, repeat step 2. The third step in the procedure is to correct for any angular misalignment by looking down at the coupling from the top view. This procedure is similar to step 1, but the gaps at the sides of the flanges are measured instead. If there is any difference in the gaps, loosen the retaining bolts slightly. Then adjust the motor until the measurements are within the required tolerance. Use a lead mallet, a brass hammer, or a regular hammer and a block of soft wood to tap the driver into position. When repositioning a motor, never tap on the motor shaft. If you do, you may damage the bearings in the motor or bend the motor shaft. The fourth step corrects for any parallel misalignment, as seen from the top view. To do this, place the straight edge along either side of the coupling flanges. If there is any clearance between the straight edge and either of the flanges, move the whole driver unit until the coupling is in line. At this point, step 3 should be checked again, because in moving the motor for step 4, it's easy to disturb the angular alignment. Repeat steps 3 and 4 until both are within tolerance. Then, tighten down all 4 retaining bolts. The fifth step in the procedure is to go back through the first 4 steps one more time to be certain that the alignment is still accurate. Do not leave out this step. Now, let's take a look at the same procedure, this time using a dial indicator. Mechanical dial indicators have 2 different kinds of probes, a plunger probe and a lever probe. The plunger probe is the pin or plunger sticking out. When it's pressed, the needle on the dial shows the measurement. The lever probe has a small ball on the end of the lever arm. When the ball is moved, the dial needle shows the measurement. Both of these probes are used to align a coupling. Dial indicators are delicate precision instruments, so you should remove the indicator before you make adjustments to equipment. Just as in the feeler gauge method, the first step is to check for any angular misalignment from the side view. The dial indicator's lever tip will be used to measure any difference between the gap at the top and the gap at the bottom of the flange faces. Start by making match marks across the top of both flanges. These marks help you to keep the flanges lined up. Place the tip of the lever at the top of the face of the driven flange. Press the lever tip against the flange face until the needle is moved to approximately 1/2 of 1 complete revolution. Then, readjust the dial face until the needle points to 0. This allows readings to be taken in both directions. Now, rotate both coupling flanges halfway around 180 degrees so that the match marks are at the bottom. You may need to use a mirror to get the reading. In this case, it's .006, or 6/1000ths of an inch. The reading on the dial face is already the difference between the gap at the bottom and the gap at the top, so you don't have to subtract to get the difference, as you did when using the feeler gauge. Just measure the diameter of the flange, in this case it's 4 inches, and the distance between the bolts at the front and back of the driver unit, 7 inches. To determine the shim size, divide the flange diameter into the distance between the bolts. 7 inches divided by 4 inches is 1.75. Multiply 1.75 times the gap difference, 6/1000ths, to get 10/1000ths of an inch. This is the required thickness of the shims. Since the needle moved in a clockwise direction, the gap is larger at the top, so shims go at the back of the driver. After inserting the shims, tighten the retaining bolts, then recheck step 1 to see if you are within tolerance. If not, repeat step 1. The second step is to check for parallel misalignment as seen from the side view. The dial indicator's plunger tip is used to check for parallel misalignment. First, turn both match marks back to the top. Then, place the indicator's plunger tip on the rim of the driven flange. As before, depress the tip to half its travel so that you can read it in both directions. Zero the dial face. Now rotate both coupling flanges halfway around, 180 degrees, until both match marks are at the bottom. The reading is twice the required adjustment. In this case, the reading was 8/1000ths of an inch, .008. Shims for all 4 feet should be half that, 4/1000ths of an inch, .004. Insert the shims. Tighten all the retaining bolts. Recheck. Then repeat step 2 if necessary. The third step is to check for angular misalignment as seen from the top view. Place the indicator's lever tip at the top of the driven coupling flange face, depressing the probes for approximately half its travel as before. Rotate both driver and driven coupling flanges until the match marks are both on one side. Then zero the dial face. Now, turn both flanges halfway around, 180 degrees, until both match marks line up on the other side. If the dial moves more than the required tolerance, remove the indicator, loosen the bolts, and swivel the driver into position by tapping on the front or back. Then repeat step 3. The fourth step is next, checking for parallel misalignment from the top view. The dial indicator's plunger tip is used to check for parallel misalignment. Place the plunger tip against the driven flange rim, then rotate both flanges until both match marks are on one side. Zero out the dial and turn both flanges halfway around, 180 degrees, so the match marks are on the other side. Remember to remove the indicator, then adjust the driver unit until the coupling faces are within the required tolerance. Now tighten all the retaining bolts. The last step, step 5, is to confirm the first 4 steps and make adjustments where necessary. Here's one other important thing to remember. After completing the alignment, allow the machine to run long enough to reach operating temperature, then recheck and realign if necessary. Frequently, when there is a wide difference between the operating temperatures of the driver and the driven units, the original alignment may actually require a specified amount of misalignment. This may be the case, for example, when a large motor drives a pump. The motor may expand several thousandths of an inch when it reaches its operating temperature, but the pump it's driving may not expand at all because it's pumping cold fluid. The units will be out of alignment and wear out much more quickly if they are not misaligned by a specific amount when both are cold. In this lesson, we have seen how to align couplings using 2 methods, the straight edge and feeler gauge method, and the dial indicator method. Either method will work well in most applications if you follow a step-by-step procedure for taking measurements and making adjustments. If you follow the procedure, the couplings you align and the machinery they connect will require less maintenance and will work more efficiently.